Hey there. I just finished, after a few sessions, implementing a new type of pattern in K1 where instead of matching on the value we have, we're first matching on what type the matchee is. And this is so that we can have like specialized implementations of functions that can check what the type, it only works, it only makes any sense when we're talking about generics here. But this function inspect takes a T and then it dispatches to very different code based on what type it was given. And it's able to bind and it's able to have patterns inside. And the main use case for this is something like if I had an equality function and I wanted to do something special for bytes, but do something more generic. If the type was not a type I knew about, I can just specialize inside an implementation really easily. So, yep, this is the finished product. I'm pretty happy with how it turned out. The syntax, it works. It fits with the rest of the language. We pass types in square brackets, and then we have a pattern following. So I think it's pretty intuitive. I'm glad I added it. And there was a number of hiccups along the way while implementing that you can, if you're interested, you can watch me stumble through it over the course of a couple days and ultimately get there. So yeah, enjoy. Hello, everyone, or no one, whoever's there. Today, I would like to add a fun feature for the first time in a little while to the language. Audio levels, such looking pretty good. All right, so I didn't clean up before I hit record, so let me just pull up the sketch of what I'd like to be able to write. So for a while, I have felt close to being able to write generic functions that can specialize based on what T actually is. Now, I'm not talking about constraining that T has implements some functionality and then using it. I'm talking about providing different code based on what T is. And you can imagine, let's just do, this is solved another way for equality specifically, but let's pretend we don't have type classes. And we're trying to do an equals function for all buffers. Buffer equals, okay, over T. And then we have buff1. Whoops, let's go big. Buffer T. And then we have buff2, which is a buffer T. Okay, bool. And what I want to do is if T is a scalar with no padding, right, where bit for bit means equal, and might not even be the case for float. So I would specifically want to check if it's one of my integer type, U8 through U64. Maybe there'd be some other types too, right? Then I want to run memcopy because even if it's 32-bit ints, then we're allowed to just compare that entire memory range. We know that it'll all be the same because there's never any padding in between the elements. So we can do better than the generic, which would be iterating over these buffers and doing an equals equals on each item. Now let's set aside for a moment the fact that that loop could just get optimized into a memcompare. Sorry, I said memcopy, into a memcompare anyway, right? We're talking about optimizing, specializing things based on what we write, and it's not always going to be something that the compiler could optimize out. It could be something that only we know about the types. So I would like to be able to say if, and the hash means compile time, right? Because there's a compile time branch, not a runtime branch. There's going to be different functions for each T at runtime. If T is U8, right, then I want to be able to write some code in here. I have a buffer U8, right? And this is all well and good. This isn't hard to do. It's just a cast, but there's a lot of problems with this code syntactically, and it doesn't actually work with the language. So the first problem is this is pattern matching, but this is just a variable name. So I need to say that I'm talking about the type for one. And my idea here is to introduce a new pattern kind. So if we look at the pattern kinds that we already have, we have literals, variables where you provide a name, enum patterns, structs, wildcard, which is the underscore, which could just be a variable pattern, but I treat it separately. Reference, We're talking about a pointer or a reference type, and then I've added type. My hope is to add a type pattern where this would only be useful to do at compile time, but it lets you talk about the type. And moreover, you get to assert on what the type of T is, or the type not of T, but of your entire discriminant, or like the matchee scrutiny, which is important. Sorry, not that, not T. So instead of talking about T, I think what I want to do is talk about a value here. Now this is interesting because it means if you don't have a value, then it wouldn't work. But my current plan would be, so we're going to say if buff1 is, and then the pattern here, we need some syntax that tells the compiler we're doing a type match. And my thought was just to use the word type and then provide any type expression inside here as the type that we're checking for. And then the rest of the pattern, and this is all still the pattern construct, would be an inner pattern. Pattern matching, typically a lot of patterns take another pattern. And what you would get here is it would be a pattern over if the type condition holds. So if the thing is the type that we asked for, then this will be a pattern over that type so that you could then further work with it. So you could just give it a name, byte buff, and this will be the most common thing. So in this case, it's going to be if buff1 is type buffer u8. Okay, so that's our type expression, byte buff, which means that now inside of this match, byte buff has type buffer u8. So I've achieved like the cast and the check in one. That's why matching is such a good place to add this feature, because matching really is nothing but a pretty way to combine a check and a cast. Else, the generic implementation. Does that make sense? So let's do a type now. Yeah, I think we need to do it on values so that we can cast the value. If we wanted to match on types alone and we don't need to cast a value, then I think that we can already just do if. So the scenario is we just want to specialize on T, but we don't even have a value that contains. So we're just going to take like a name string. I don't know what this function would be doing, but it takes some type T and a name, and then it does something. Maybe it's some metaprogramming thing. I think that we could just say if type ID T equals U8, and then specialize this way. The problem with this is you end up with values, and it may be that you would actually want, this is not a very concise way to express that T is U8, but without doing something first class, like a type switch or something, type switch, the thing here that makes this hard is that now what we need here is a type expression, not a value expression. So that's why it would have to be its own construct entirely. So comparing type IDs, okay, but this can just be a helper, right? Type eq, right? A, B. If that's all you care about, and this will compile to a literal constant Boolean, regular function that you could write. And I think I'm pretty happy with that for type level where I don't have a value. So let's return to the value version. Ultimately, I want to do a switch here. I don't have pound switch yet. You can do a static and then switch, which will run the switch at compile time. But the problem is that you're just going to produce a value here. What we actually want to do is do only the branching at compile time and then insert the runtime code, which is what this special case if does. That's why we have pound if and we don't rely on static if, because static if, and then we would need to then do something like insert or something like just insert this code, right? If it's true, which, you know, might be good, but this feels better anyway. So, you know, we have a static for as well. So I think we're going to have a static switch. All of our major control flow constructs, having a first class static version makes sense, where we're doing metaprogramming for those. We're not generating like a value or a constant. All right, so let's do an example where there would be an inner pattern. And for that, we're going to do a point struct. So instead of buffer, let's just say we have T's. inspect. This is going to inspect T, right? V. I'm going to call it V. So we have if V is, and here's our type pattern, type accent YAnt, and then we're going to give it a name. And the point here is we could give it a name, struct, right? And now struct is a variable inside here. Struct is of type. It's of that struct type, but we'd like to be able to pattern match in here as well. So we could do this simple pattern and print line. And let's go even deeper with like a lot of nested patterns. X was 3. It was a point, and X was 3. Okay. This is the type of thing we'd be able to write, was a point. Else, if, and this is where we would want the switch, but that's just a separate feature, so I'm not going to worry about it for now. So we have to do another pound if to make sure that this entire part also runs at compile time. V is type, but we have a different pattern here. It was a point, and X was not 3. I think that's sufficient for me to be happy with this. And then we'd say it was some other type. And then let's just go ahead and print the type that it was. Types type name T. And this doesn't parse because we gotta implement it now. All right, so that's it for the intro here at 12 minutes in. Here's our type pattern, inner pattern, type ID. I think that's all it needs. It looks like they all have spans. Okay. What? It's amazing how I just actually can't see what I'm doing when I'm... And we're just gonna walk the errors. Binding actually should be the right thing now. Inner pattern. But it's not. So actually this is just recurse. This is a function that returns all variables bound by a pattern recursively, and the point is to make sure that two given patterns bind all the same variable name so that you can merge them into one arm. And I don't even know what this is. Pattern has innumerable literal. Does this pattern have an innumerable literal? Well, it does if the inner pattern does. Format this. Okay, well, we're compiling now, which is great. I think I want to go ahead and parse this pattern. Parsed pattern. Yep, let's move back to the parser. Type. We got a little bit ahead of ourselves. Parsed type pattern. We're going to go to here. These are actually identical except for a type ID. Parsed type expression ID. Okay. Now we gotta parse it. It's never constructed. So let's do it. Fun parse expect pattern. Expect parse pattern. Loop for postfix. It's gonna be part of the base pattern, and we try to parse a literal atom. Ooh, we're doing the like most expensive thing first. Kind of. Yeah, ident here. It would be better to probably check for open brace dot first, and then we do ident again. Yeah, this parsing could go in a bit more efficient order. This is going to be a more expensive function. It might not even be helpful. It's because it's factored out from other literals, which makes sense. When you try to reuse parts of a parser like this, that's where things can get kind of tricky. Because the order that you check things is really important, but I can't know everything I'm checking inside here, and if it might conflict with like an open brace case, like without actually going through them. So it's a very leaky abstraction, if you could even call it that. So here it's like, oh, okay, it does check for identifier first, but it only does true and false, and then otherwise it falls through, right? And then down here, after we've checked another bunch of cases, we're also checking for identifier. So yeah, anyway, we'll put it here because that's not really our problem right now. Oh, it's also going to be ident though, because type keyword type. Yeah, type is not a keyword. So let me take this opportunity to think a little bit about my syntax and decide what I want to do here. I'm fine with this. So we'll check for ident. It's not in literal atom. It's down here. And then we should be, all right, I actually have a helper for this. This eats an ident and then in turns the identifier. This is going to be expect ident. And ooh, we could require lowercase, which would fix a bug. Yeah, I'm going to do it. Not a bug, but one of my to-dos where you accidentally name a pattern instead of doing an enum pattern if you forget the dot. Okay, and this is going to be ident token, and this is going to be ident, and then we can drop this, and then we have the name. So we're going to do let tokster is going to be better. Oh yeah, right, is the name. We hang on to the borrow. See, this is where we special case the underscore. Maybe the parser is not the right place to do that, but maybe it is. It's probably not important at all. Type. Let's just do it this way for now. Eventually we could switch on this. Yeah. That's fine, let's do it. It's gonna scale a little bit better as the code grows. It's a little bit easier to read as well. And the other thing is, in this case, we're gonna have to require the brackets too. That's okay. All right. Self.expect token k open bracket. Let inner pattern expect parse pattern. Okay. We close it out. Type pattern, close it out. And now we need our binding. Oh, this is interesting. Could the syntax be a little bit quieter? Oh no, because it's got to be a pattern in here. I think for now, by quiet and noisy, I'm usually talking about number of like symbols. I'm talking about requiring these parens or not requiring these. But, let's just require these parens. So. And this is the type ID. Let's parse a type expression here, and then let's parse an inner pattern in here. Okay. Type. Let's make a parsed type pattern with inner type expr and span. Self.ask patterns add pattern. And that's how you do that. All right. Span. How am I doing the other spans? The ident token? No, it's bigger than that. It's going to be the ident token all the way to the end. Self.extend to here, ident token span. All right, we parsed it. Now let's go implement dump. We would need to do the AST dump display pattern. Let's compile the pattern first and we'll print that. We'll just hope we parsed correctly. Eval pattern. Right, this is compile pattern, kind of. It's compile pattern into a typed one, not into code, runnable code, if that makes sense. Not a lowering. It's a typing, not a lowering. Parsed type pattern. Okay, so our requirement here is to produce typed pattern ID. Self.patterns add typed pattern type pattern. How many times can you type pattern? Like that. Okay, typed pattern ID. Can fill this out. It needs an inner pattern, type ID, and a span. This is a pretty trivial compile. This is kind of fun. So we got to compile the inner pattern. Let's look for something else that is compiling an inner pattern, right? Oh, I see. You want it in, no, it's not in inner pattern. Type the pattern ID. Oh, it is. Oh, that's just how I get it anyway, though. Eval pattern. What does it take? Pattern expr, we have that. We parsed one. Inner. Target type ID. This is the fun part. So it's a pattern over what type? Well, the type that we were passed. So we got to do the type ID. Type ID. And this is going to be eval type expr, which we haven't done yet. There are no patterns that have type expr, at least not directly. So this is fun. Parse type pattern type expr. We need a scope. We have a scope. So that's great. And then that's the type. And if all passes, then this pattern should be a pattern over that type, right? Exactly that type. So that's our target type ID. And then our scope ID is the one we have. Yeah, I think that's fine. Allow bindings, true. Oh, allow bindings has been given to us, and we're not gonna say you can't have bindings here. Missing a closed paren. There we go. Now things will format again. We're gonna just copy this because it's small. It's like 24 bytes, I think. It's 12. Yeah, we're just gonna make a copy. All right, and then so that's our inner pattern. So the type ID of a pattern usually that we produce. So in this, like a reference one, it's the reference, the inner type. What type ID? Oh no, they don't usually have a type ID. Only this one does. I think that's all correct. So we've compiled our pattern, and now let's go implement the pretty print. Let's see what AI can do for us. Close. Right, stir type. Just gonna reverse everything we just did. That's gonna be closing and then opening, which is fun. Display type ID, right, type pattern, type ID, expand, do we have that? False, for sure. Okay. Display pattern. What do you want? You want the pattern and then the writer. Type pattern, inner pattern, right. It is called writ. But you know what? It should be called W. All right. Let's run it. Variable patterns that they can't be uppercase. It's that they can't be. That's gross. Let's just make a lower. I'm not typing false true. Let's run it. Okay, that's it. If lower, I think underscore is like, yeah, if upper, let's see. That's the only way you can begin an identifier besides letters. Can I program? Just making shit up. If it's not underscore and it's not lowercase, but you wanted lower. If you wanted upper and it's not an underscore in there, capitalize. Little sidetrack here. Oh, and it works. Okay. but we're not doing anything yet. On compile pattern into value. Unreachable. So what is it doing? It doesn't seem to be ever actually parsing our patterns. So let's start printing them. Yeah, we should be getting like a hard a.k1. Are we just not compiling? No, we compile everything. Ah, okay. So let me tell you what's happening. Maybe I should still be type checking this code though. No, we're not going to look at it. So when you're doing generic programming, like you're in a variadic, a parametric function, and then you run code at compile time, which this does, it at least runs the condition at compile time. What I've realized is I just don't want to run it at all, because until we know T, the result of running this is unhelpful. So we're actually going to, when T is just T, for the non-specific pass, what I call the generic pass, which happens once, we're going to check this body, we're going to check the function body and not execute any compile time executed code. So we're essentially going to comment this out. So we need to call inspect with at least one T. Inspect. All right, and it just takes a value. That's kind of fun. X3, Y, 10. And do we win? Bindings are not allowed here. Cool. Because it's an is match. Why? I usually allow bindings because it has an else. I'm really not sure. Because if I were to say, oh, it's because this, okay. Because this isn't our normal if, this is the static if. The way this actually gets compiled is this is just a Boolean expression. And then this has no relation to this. So we actually, it's correct that we can't make bindings here because this pattern isn't attached to a right-hand side. So doing this, creating bindings with static ifs like this isn't gonna work. In fact, I think that checks out because I think I have to do some special things to make it work in the non-pound if case. Like we have to evaluate this in light of the fact that we're inside. And if we did a switch, it's better. Because with a switch, the right-hand sides are definitely bound to. So let's get further though. That's the limitation, which is sort of a separate issue. So let's get further without creating bind. Am I allowed to use underscore? All non-literals, yep, this is perfect. So because we never handled it in compile pattern. So if we go back to typer, compile pattern into values up to here. And this is just going to be to do, compile to values, and hopefully I have pattern to string. Pattern to string, pattern ID. Hopefully pattern ID exists in scope. What are we matching on? My bad, pattern, it's called pattern. Okay, so now we should get it to do with the dump of our pattern. Compile to values, type, $492. What? That's the pattern ID. Bum, bum, bum. For struct patterns, I think. So we go to dump, display pattern, literal integer. Oh, value is a value ID. That's a string ID. Let's fix these. 1. Bool. Oh, let's just self.display value. Static value. W value ID. It's going to be the same for you. Display string ID? No, I don't know. That's fine. Run it. That's our pattern. It's fully compiled. We have to compile this into instructions. So the code that you would write if the language didn't have pattern matching is the way we think about this. So our job is going to be to emit instructions, something like comparison on type IDs, and then like a hard cast, a transmute cast, so that you get a typed term of the correct type, a variable of the correct type bound. Yeah, Yeah, that's right. Let's go ahead and do that. Not worry about our syntax problem where we can't actually get bindings. Okay, let's take a look at some of the other. For a variable, we do a variable definition, so we don't really need to worry about that. All we need to worry about by deferring to an inner pattern is great. We just have to check, we just have to do the type check. So ultimately we're gonna wanna push matching condition instruction, not binding, but a cond. At the end of the day, we want to push a cond to insters, representing whether the type matches. Okay, it's going to be a trivial check because again, this is going to be like specialized. Let type eq. I could just do a Boolean. I can check it right here. That might feel better, but then like the printout of the code won't look quite as good. I can send the call to the equals function and the call to type ID, or I could like do something better. So we have type T, and I think that we should have a type. Our target expr has a type. Yeah. Let target expr type. And that's that. And let me just check above if anyone's doing that, if we already have it. Target expr. Oh, we already do it. Yep. I thought maybe so. Target expr. Now the question becomes, are we doing a hard equals on the types or is it a subtype? It has to be a hard equals, the exact same type. I think so. That's crazy. We'll send the Boolean at the span of this pattern. Matching condition instruction cond value cond. Okay. Compile the child. It's just our target expr. We're matching on the same thing again. It's just been casted. And that's how we compile this. Let's print out this type calculation. Type like this. Let's run it. They're the same. Missing variable. Cool. Okay. It looks like we're miscompiling. Well, we're failing in bytecode generation on a missing variable error. So let's improve that error to log which variable we're trying to access to try to figure out what's going on here. It looks from the span like it's here. And I guess maybe that does make sense if v is not statically available. Yeah, I'm pretty sure it's v, and I'm pretty sure I know why. So the idea is if, we already established that this entire expression is running at compile time. And it's technically depending on the value v, which isn't known yet. We know its type, and all it cares about is its type. But strictly as written, this code is not going to compile because it's going to try to evaluate this expression. Basically, inside of this scope, v doesn't exist. V shouldn't be used because we haven't made it available static. So that's a big bummer. And all I want is its type. So we kind of hit a bit of a snag with the design plan here. I could make every variable available if we're only talking about its type, but the notion of if we're talking about its type doesn't really exist here. The issue is this expression here. I mean, this can be any expression, and we're saying v, which is a variable expression, which is going to look it up in scope and it's going to evaluate. I mean, this could just as easily be 42, which is an expression, and then it would be false, right? Let v equals hello, right? v2, say. If v2, we know the type of v2, but we don't know what v2 is, so we can't run this static. We could try to run type of v2. Now here's the problem. That runs v2, and it results in a type expression. The left-hand side of a match has a value expression. So now I'm back. Sadly, I'm back to wanting to branch on t and take a type expression here. But now this has to be a different thing than the normal match syntax, which takes an expression here. And moreover, If I do that, then I have no way to get at the casted value because we haven't talked about V at all. The whole plan might have been a little misguided. Now, when something like this happens and it feels like it should work, it's worth really thinking about, like, can it not work just because of a limitation, or is it because my plan was actually nonsense, right? If V, so what can we do? We don't find this variable when we, right, but we don't actually need it. Oh, okay, this is also interesting. This definitely talks about the value, which we don't have. All right, so walking back, what if we just remove this, okay? Which means that this is going to be runtime code. Also means we're gonna type check it in the generic path. That's okay. This is going to become a static false, the way we've written it. We can still achieve the behavior we want, that it's compile time branch, because the condition will be a constant. We could even go further and compile this match out entirely. The problem is if some of the patterns are type patterns and some are value patterns. So if we get later on to switch, it's a better example because the else ifs, they're all independent. If we were going to switch V and we had one type string, right? And here V is a string. V is a string now. Okay. And then we had hello, which needs the value of V. And this doesn't, but this needs the value of V to bind. So we always need the value. So, two options. I have a way to pass runtime values into compile time code, which is I would pass V in here. And what that does is it signals to the compiler to try to make V statically known. In this case, it's a parameter, so it won't be able to do it. And what's more, we don't we'll know the type. By the time we actually run this, we'll know it'll run only on specific, but we'll never have the value. So doing this here never makes sense. We'll only have the value back in this realm, right? So it doesn't make sense to have a nested pattern here if we do it at compile time. It only makes sense to do the name. You can only provide a name. And this starts to become such a special case that it shares nothing with static ifs, with other static ifs. And it just doesn't work because you're allowed to say and here and provide another pattern. So I think it just doesn't work. But if I do it at runtime, this is just gonna become a true and compile right out. And I can even, let's do it as the switch version. This becomes true. Let's remove this. So this will be, T type ID T equal string, and then we'll do our cast of V, and this will just be V equals string, V equals hello. This will become V equal hello. Okay, and I think we'll say that this doesn't eliminate any cases for exhaustivity analysis. These don't count, just like these don't count. All right, so let's just try to do it at runtime. No, if it's not a string. Oh shoot. I think this is going to say, yeah, we're matching on a type variable. So this is going to say that type int will never match type variable, which is super interesting. But you could do this, and then you could say 40, and then you could say V was an int, and it was 42. And now let's do type int x. We'll name it x. V was an int, but not 42. Okay, this is going to be our example. Wow. Okay. Inspect. Hi. I like the struct too. Let's add the struct case back. It's too fun. How about that? V is V. Print2 is self T. All right. So it makes a binding and we just haven't done the cast. Oh boy. We want to run our inner pattern on the casted. We'll make a binding to that. We'll synthesize a cast on target expr to type ID of cast type transmute with a span. It's fine if the span is, oh no, let's do the pattern span. Okay. T.type ID, target expr type. T.span. I thought I was copying T. Love you, Rust. Love it, love it, love it. And that's compiling. So what are we doing? We're now running our inner, we're doing what this was always meant to do. When we run this pattern, we're running it on not V, or the variable that holds V, but we're running it on the variable that holds V casted to this type, because we know it's this type because we just did a type ID check. And I think that we should print out eval match. I had like a big debug for printing these out. Match expr. Be nice to print the whole. Maybe we can do it. This is supposed to be how I print things. Ooh, failed type checking. We're never going to be able to find the error, but let's look at what we've generated. Oh. 42. So this is main. Oh, statics. That's going to throw us off. All right, we're in debug. We're stuck in debug mode. We're only supposed to be debugging inspect. This is just going to be way too much output. So the binding isn't working. Let's use a different name. Let's use a different ref. I don't think I need to make a scope or anything. Variable makes a binding. ctx.scope. I feel like everything should be okay here. And go ahead and call it VV. VV should definitely have priority anyway. Yeah, self is T. Target expr type. It is. Oh, we're type checking this. Target expr type. Oh, so in this case, it could be false. Target expr type is T, and it's not string. So this is happening when we type check this code while T is T. And what I was hoping is all of these would be false. We just need to cast it to the desired type, not to the target expr type. So we're always casting to T.type ID because that's the pattern's type. And now we've copied all of T. So let's just do like T.type ID, T.type ID, synth bool, T.type ID, T.span, So in the case that they're not equal, it matters that I say we're going to cast it not to T, but we're going to cast it to string. And that code will never run because it's guarded behind a hard-coded false. And what happened to inner pattern? T.inner pattern. Ah, unhandled patterns, TVAR. This is supposed to print more things. It's supposed to print that the match is not exhausted. Like one unhandled patterns. Yeah, I got you. Gross, but it's actually not that gross. Is that the best I can do, by the way? Is that all I know about it? I probably have its type ID and I'm losing it somewhere along the way. But the point is that it's saying the match isn't exhaustive, which is completely true. And let's do this. Like we did the last. It's that one. This pattern handled no. I like that. So the uselessness check. Useless. 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 Useless pattern. Has enumerable literal. We can just change this to be has enumerable target. Type pattern. Immune to uselessness. Pattern never useless. Because if we're matching on types, we're never going to be exhausted. But I think that we can still, maybe we can still get exhaustiveness in here. That's the part I'm fuzzy on. you gotta handle that. And then you still have to handle this. So how would I do only a partial? If I were to only check when x is 3, then this would only be partial and it should complain. Ah, x is. So there's that one. And then, now that handles them all. Let's just run it like that. Not yet implement. Bytecode to, it's probably a tree. It should, this is the wrong comment. And we have to store, we always emit a bitcast instruction, which I don't love. I'm just gonna copy paste this for now. We'll just keep it as is, cast strings mute, just for now. If we happen to be given a destination, then we have to store it there. Otherwise we just have a node that indicates the type, which might be used. Like I'm not really sure, but anyway, back to typer. All right, we got all the way to LLVM code gen. Oh, and we got true on 2 calls with int. I would have expected a couple more trues. I would expect true. Well, the ints, yeah. So we'd have to cast that to regular string, not a statically known string. We could make the type checker follow static, and then we should get a true on the string. And I would just like to see a true, yep, and we see a true on the struct. So it's all working. And we generate bytecode, and then we get down to here. We have an int value where we want a pointer. That's great. Probably something what we just did with the bitcat. It doesn't make, I can debug that later. We're generating something silly. I'd like to see the code. Maybe be careful what you wish for. Inspect on I64. Is this the one that crashes? 99 instruct. We're just casting a struct. It says v is an int, and then we're casting it to a struct. Oh, the code will be bogus. That's not what bitcast does. I think we just want to do nothing. Yeah, I'm gonna add a full-blown like no commit here. Reconsider all of these cast types. For this one, all we're doing is the storage that we might require to complete no off storage. Ugh. All right, we do need the type that we're casting to, but that would make us, would that mean that we're storing an int, like possibly an int to a struct? What I'd almost rather do in the cases where I know it's false is just generate an unreachable, right? Yeah, this is all dead code. And we're just trying to get the dead code to be valid. Compile pattern into values, type. So I have a bool here. If it's false, then I don't want to do the trans. I just want a single unreachable on the right-hand side. So it compiles to like if switch false unreachable, false unreachable, false unreachable, true. Yeah, no, that makes sense. And it needs to be that general because not every pattern has to be a type. Like one of these could just be a normal pattern and that would need to still work. So you'd have false, unreachable, maybe true, some actual logic, and then, oh, wait, that's all I want to do. So instead of like this, we don't want to synthesize a Boolean. We just want to be like if con. Well, we still can. And only if conned do we even bother? Conditions binding. We don't need a binding. Well, then the inner code is going to reference a variable that doesn't, but we're never even going to compile the inner pattern. But the right-hand side will try to reference the variable. But we should just not compile it either. I don't have a way to say for a pattern, don't compile its arm. We do this, and then we do its guard, and then we do its concept, which needs to be valid. It's tricky. I guess I could just return an error or something. I can make a new one of these that says we're bogus. All right, if there's ever a hard-coded false conned, we could even do it. You could even express it more clearly. Then you could just always skip the arm altogether. It's like some pre-optimization and it solves the problem. I don't hate that. We can't just skip doing this because then the right-hand side code won't. We can't avoid casting it because it also won't type check. What are we returning? A type of result of a unit. So we would need like to return, or just make an enum. It says whether it's dead. If I can scroll past this to show you what I want to do. Yeah, here. We're switching on V, and we're gonna have const false, 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 and then the fallback, which has no condition. All right, and this is inspect on T. So they were all false. And here's inspect on false, false, false. It's the same thing. I'm looking for inspect on one of the types where one of them is true. False, false. Well, we can use this as an example. So the idea is just to eliminate all this. Don't even have this on. But it's like now it's a required optimization. Optimization. Just of the tree, not of it like the code that runs to make it correct, which is weird. And what is our actual error? We're getting down into the LLVM and we're breaking contract by asking to bitcast. Let's say it's the case where it's the struct, and in this code, even though it's dead, because this will always be true, we're bitcasting the struct to an int, which doesn't work. It's just an invalid node for what bitcast is supposed to do. Now I'm not doing a bitcast anymore. So then what happened when I removed that is it now just like the CodeGen actually chokes because it wants a pointer, or it wants an integer because we've typed it as an int, but it has a pointer because it's a struct. So we can't really generate any code that wants to handle, or we could do a proper bitcast. We have a bitcast operation that would correctly handle that. It would still be bogus code because, well, it's not an int, it's a struct. So you would be interpreting struct's address as or something similar or worse. Yeah, you'd be interpreting, or maybe loading, maybe the first. It would be bitcast aggregate to scalar. So if they were different sizes, it'd just be bad. Yeah. It's easy enough in the types tree to just like, hey, just do a transmute, change the type of the thing, and it doesn't matter. But then when you get down into like CodeGen, it doesn't like that. We could use a different node, just like dead. No, I mean, that's what ultimately we're trying to perform a load, I think, right? Well, it's a simple thing at the end of the day. I mean, this is working. We just need to pick the most elegant way, the least bad way to not generate code that we choke on later. It's dead code, so it doesn't even matter if it's correct. It would be nice not to rely on eliminating the whole arm. We found an int value. Which code exactly? I wish I knew exactly. Copy. Makes sense. So we're generating a copy instruction of some trans. What is this one? I don't print it. I don't print this. It doesn't. We should print both types. This is the main copy I see. Okay, and it's the fulfill. It's casting it to a string. Maybe that one would be fine. Load nice64 now. Okay. Load nice64 from you, because that's V. So this is when V is int, and we're casting it to string, and then we're trying to do a copy. Yeah, I mean, I'm glad it blows up. I thought I removed bitcast. Oh, right. We don't have 2PT. Okay. So it won't be a bitcast. It'll just be, it's an int here, and we're going to store it, strings storage, which would be terrible. Okay, it's one of my errors, and it's clearly not incorrect. Copy, oh, we got a lot. Copy source is not a pointer. Okay, so we clearly can't just, I just need like a fake value of the correct. I could do that with an Alloca and just never store to it. Probably time to take a break. Okay, picking back up. On the next day, I probably worked like 15, 20 minutes on this, maybe 30 since I last stopped recording. And we do have a working output now with V is a 0.310. We see V is hello. V was an int, but not 42. And V was an int, and it was. So the approach that I went with, to not have any of the subsequent CodeGen phases choke on the branches that we'll never take, was the following. We want to be in this compile pattern, this type pattern. So what I have gone with is we still synthesize the Boolean, and that is the instruction. And if pattern did match is what I'm calling this, right? So it means that the thing we're matching on is the type that the pattern wants. Then we're not going to cast at all. And my thought was this would be like a no-op cast just to the same type in the happy path and in the sad path. But this is better, right? Because the whole point is that we're asking is is v of this type? And if it is, then it's already of this type, and we can just pass v straight on into this pattern. I think I was getting caught up on the fact that v is of type t, but by the time we're specializing, it's not. T has been substituted with that struct type. So it's a no-op for what we pass to the inner pattern in the true case. And in the false case, the most obvious and great way to create a garbage value of a given type is actually to call a function that returns that type, but internally the function just calls exit. So this has some nice benefits in that, it's like unreachable. Like if this code ever does get called, we're just gonna immediately get a crash and saying something like unreachable or phony value should never be called, but it's perfectly valid code. And we get in the case that t is the struct for this arm, VV is going to be the result of calling phony of string. And I've gone ahead and written it as a regular function and built in. Phony of string is just going to give you crash phony. But the thing is with bytecode gen, that's fine because we're not going to inline this. We're not going to go into the function. So I guess if we ever did inline this function, we'd have a terminator there, and that could be a big problem. This function boundary is doing a lot of work, and I know this is something that is done commonly, so I need to weigh what I would do there, because I do plan to start inlining things. Anyway, I mean, the insight here is that if something exits, then you can say it's whatever type you want because you're never going to get past that. If we were to inline the code, though, I think maybe we still just cast the crash so it doesn't look like a terminator. Yeah. Unclear. I think you do. I think if you inline this, then you need to include the cast node where this never, crash returns a never, I don't know where it is getting casted to the T. And then maybe you have the same problem, but because it's a never, maybe it's cleaner. For now we're good, right? We generate a phony and we match on that. And then now everything runs really happily. But again, and one thing I wanted to clean up was the fact that we had to unstaticify this. So I don't think we're going to support talking about statics in here. So I think that I want this to work now. And we can go ahead. Whoops, that's wrong. Yeah, view was something else. Static string hello. So I kind of want to fix that. And the way I'm going to do that is I'm going to look through statics to the inner type here. So if you do one of these matches on a static, I think I'm going to erase the type, because now would it ever be useful to actually be able to check? I mean, it would allow you to do things like this. Because that's a specific static string. Oh. Okay, so maybe instead we're going to do something with this type. If the pattern type is a static, then we won't erase it. But if it's not, then we will. And I think that's pretty much going to do what the programmer wants at all times. So target type chaste, sometimes I call this. Pattern type is static. Match pattern type as static. Target expert type. Otherwise, so the user spelled a static, in this path. And I don't even know if I allow that syntax, but they could just write quote hello. If it's not, then it's going to be self-type get. I just want to be sure to follow it, get chaste ID. So what that's going to do is it's going to chase through statics. So, okay, in this path, the user just passed string and the actual value is a specific string. We want to match. And then I'm gonna comment that the user passed string and the value is a specific static string. This should pass. All right, and in this case, the user passed a static as the pattern type. We should not chase through the static on the scrutiny. Target type chased. And then we need to phony to the type that they asked for. Yep, always to, because this is on the target, always to pattern.typeid. That doesn't need to change. Okay, so now we have a few cases that should work. This, hello, type, V was the static string hello. V was some other string. And we'll print it. And we'll print this one too. Okay, V was an int, but not 42. In fact, it was. Okay. K1 reload. Can we reload the LSP and get rid of our red line? Not sure if it'll work. Oh, that's slow. Come on, compile. Oh, yeah, looks good. Ready? Oh my goodness. First try. It was a static string hello, hello. V was some other string. Oh yeah, duh. So first we're going to erase. Erased, erased. It's called static erase. Did I call it from static? Typer from static. Yeah. Oh, in this case it's not. I don't know. Something's kind of weird with how inference works. When I choose to type this as static and not, it's still an unfinished thing. So we'll do it this way though. It's going to be V was some other static string or just a runtime string. And then we'll do a static string hell. Don't know why U of M's mad at me. V was a static string hello. V was some other static string or just a runtime string hell. V was some other static string or just a runtime string. It's because we've chosen to drop the type info of hello. So the only type that inspect sees is string here, so it's correct. Okay, so all of this is good. This lets us dispatch on types, which I know this looks like something you could do, like you can just do this in Java, but these aren't classes or object compile time stuff. There isn't a header to inspect, right? So it's a little bit different. And we already did have a way to specialize if you're implementing an ability, but if you aren't implementing an ability, we didn't really, because we don't have overloading. This is an important capability for the language. Let me remove the debug, and then maybe we might need to remove some other. Yeah, we can stop doing this. This can become a debug. Stat is fine. I have a bunch of warnings. Right, I added this and it's dead code, that's fine. I'm gonna do static switches as part of this change. Oh wait, we don't need them anymore for this use case, but I still think they're missing. Maybe I'll add them, maybe I won't. All right, I don't know where these colors are coming from. It's just a terminal buffer. It's really cool though. This I color, none of this other stuff I color. Huh. Anyway, I like it. And now what I did want to do was also optimize. So we made it work. So the optimization isn't needed for correctness anymore, but I kind of do want to drop every arm. All right, so let's actually go back to dumping this. And what I want is to end up with only one arm for each match, only for the type. So you see here our code has arms for each type. And here's the phony call. So we should know already that we can never get here. B17. So who goes to B17? It's going to be some false condition. Jump B17, jump B1, jump B17. Fall through cons. Where's the false? These should just have a empty condition. I can't search for the numbers here, but I kind of want to find false. It's not making sense to me. The code that actually just has a Boolean constant. Eq I262, the number 42. That's like a real I don't think we could have ever gotten. Here's a phony call. So this block, let's B17 again. Whoever jumps here, this should be impossible. I'm a fool of myself, huh? I just wanted to locate the dead code so that I could like watch it disappear, but fine. Matching con. It will be a matching con. Oh, hey, maybe. No, I don't have an optimization in here. Push jump if. Oh, there it is. Jump if false. We're optimizing it out already. The thing is, a matching condition where there's a hard-coded false, we should never generate the continue. I think it's better to rip it out in the type check, honestly. I think it's better to report that it's dead. Now, as long as it's never, it's impossible for this to be side affecting. The pattern could be, no, if the pattern never matches, then we never even run an if guard. Yeah, it can't be side effect. I think we can just strip out the code altogether. Yeah. We're gonna return a bool for now, indicate, or we could iterate over the condition. It's called in 7 places, but most of them are gonna be recursion. Yeah. This is the one from actually compiling a pattern map. So it would be from here. Yep. But that would mean not type checking the guard. I guess if we did any form of dead code elimination, it's going to get taken care of by this. It highlights it. So I don't know which type this one's for, but we jump to B3. Oh, B0 entry. Okay. We jump to B1, enter match, which is a jump to B3, which is arm1 condition, which is a jump to B5, which is the arm2 condition, because it's just false. Yep, and so we're just jumping through these falses, and there's no, because the jump if is gone, there's nothing that can lead to the other consequent blocks, and we would just delete them. So I think that they would just show up as dead code the moment we do like unreachable block check. So that's cool. Let me just add it to the to-do because it will be fun and like educational for me, much so. This doesn't really go in good ideas, but it's fine. Bytecode, prune unreachable blocks. There's a whole project for optimizing the bytecode. Where's inline? Inline. I could swear that I had put that I wanted to inline bytecode. I'd switch to bytecode. Yeah, I mean, we can. K1, are we? I guess not. Really basic stuff. All right, so if that's covered by that optimization, which is something I want to do, and I want to drop as much code as I can before I go to LLVM, just so that I'm handing less code to LLVM. It's less to do the heavy optimization on. I think it's just going to be a win. And it will make the VM perform a bit better, right? Let's commit this as a test. And what do we want to call this? So let's go in test source suite 1, and we'll call this moderate complexity. We'll say that this is type pattern. I already have a bunch of pattern matching tests. I'm okay to just have it be its own thing. No, I'm not. Pattern. Is patterns. Match. Matching if. It doesn't really cleanly go anywhere. It's called main? Yeah, it is. Let's just do it in here. Type pattern. There you go, that's fixed. And now Okay, but instead, let's return an int. No, let's just do unit, and we'll just do a bunch of assertions. X, Y. I want to assert that X and Y are an int. X plus discard. Oh shoot. No, I need to return. It's not going to test that bindings work though. What do you think? Spec 6 con 6. How do I know though? If it's 42, it returns negative 42. Any other int, it returns itself. If you give it any string, it's going to do its length. Oh yes. A non-static string, it's going to do its length. If you do a point, it's going to sum the points. So that's going to be 13. If you give it a static string, if you give it hello, you just get 2. If you give it any other string, you're going to get the length. If you give it an int, you're going to get itself. If you give it 42, you're going to get negative. All right. This is a ridiculous test, but it's covering the behavior really well. And let's do expect true, which is an unmatched case. You should get 6. I could have made enum, right? I could totally have made enum and put the value I want in there. It's fine. It's fine. Wait a minute. Does it work? Ready? All right, works. Hey, we did it. Okay. Let me cut there, and then I'll do a little recap and put it at the beginning for you, friends.